Hello, future engineers, subscribers, viewers, and students. There is a video in Strength of Materials 1 or Mechanics of Materials 1, and this is part 1. And in this video, I'm going to discuss shortly the stress strain diagram, basic stresses, thermal stresses, axial deformation, and sample problems associated with this topic. So let's have the stress strain diagram. So we have a specimen here. This is the stress, force over area, and the strain, which is the change in length divided by the original length. So this is the specimen, and as the load is increased, you have to look at the stress strain curve also. So when P is zero, it's zero. Then when P is applied such that the plot of the force over area stress to that of strain remains straight, and this is the proportional limit, the maximum stress value at the portion of the stress strain curve where the relationship between stress and strain is linear, and that's called the proportional limit. Then when the force is increased further, there is a maximum stress beyond which the material can no longer go back to its original shape and size, and we call that the elastic limit. So this point here, we have the elastic limit. Then when the load is further increased, it will reach a point where the material starts to behave as a plastic material. And there are 2 points there, the upper yield point and the lower yield point. So that's the elastic limit. We define it as the stress level beyond which the material can no longer go back to its original shape and size. So that's elastic limit, and we have the upper yield point and the lower yield point, the stress level where the material starts to behave as a plastic, wherein there's no appreciable increase in stress, but the strain increases. And theoretically, it is supposedly straight until it reaches the ultimate strength, the highest stress level in the stress strain curve, ultimate stress, and beyond that, the material undergoes what we call necking. And if the load is continued, we have here the load at failure. We call that the rupture strength. So we have the ultimate strength, the highest point on the stress strain curve, and we have the rupture strength. So next we define the what we call um, straight line portion, the elastic range. So we have the material before this rupture strength undergoes this necking configuration, and beyond that it fails. So we have here the elastic limit range, that range there, and from this point down to here, somewhere here before the ultimate strength, we have the plastic range. So that's the plastic range, elastic limit range, then plastic range. Then the last would be the range where the material undergoes what we call uh, strain hardening case. So that's the strain hardening range. And we have the ultimate strength as indicated in this figure. Now in this portion here, we have stress strain diagram. The curve is straight, so that means stress is proportional to the strain, and that slope or the constant of proportionality is actually the modulus of elasticity of the material. So transforming this into an equation, this is force over area equals um, E times the strain. That's the relationship. So this is the resulting deformation delta within Hooke's law, within elastic limit, and therefore P over area equals E times delta L or delta over L. Therefore, the formula for delta is PL over AE, and take note that P over A is stress, so it may also be stress times length over E. So PL over AE, or deformation due to this um, normal stress, is normal stress times length over E. So that's it for this part of the slide. So let's have basic stresses. And one is the normal stress, denoted by sigma sub n. This is the stress that develops on the members subjected to forces acting along the axis of the member. And this is the stress that is perpendicular to the cross-sectional area of the member. And it is either tension or compression. So it is also called axial stress. So for instance, in this configuration here, these two forces tend to stretch the body. Therefore, the resulting stress perpendicular to the section of this body would be tensile stress. And for this loading here, these loadings tend to compress the body, and the resulting stress would also be compressive stress. Shear stress is denoted by the symbol tau, and it is a stress parallel or tangential to a load. And if we have a body here that is held in equilibrium by putting it in this surface, fixed surface, this is the cross-sectional area. The load will be transmitted. One is parallel to the area, the other one is perpendicular to the area. The one that is parallel to the area will produce shear stress, resisting stress called shear stress parallel to the area, tau, and it is equal to the component of the load parallel to this section, which is P cosine theta, while the other component, which is perpendicular to that area, is the normal component, will cause compressive stress, compressive normal stress, and that is equal to P sine theta, the normal load, divided by that area. So shear stress is the component of the load parallel to that area is P cosine theta divided by area, while the normal stress is P sine of theta, the vertical component, divided by area. So that's the normal stress. Then bearing stress is compressive stress, which is developed perpendicular to the projected area, projected contact area between a rivet or bolt body and the plate. So a compressive normal stress that develops between two contacting bodies. So if we have two lap plates here, then the load on the upper plate is P over 2, the lower plate P over 2, so that's why the total is P. Then we have here the projected area of this rivet or bolt, which we project it to the right, and the dimension of the projected area would be rectangular. And the assumption is, although the body of the rivet or bolt is curved, the bearing stress is assumed to be uniform, over this projected area, and it is equal to the diameter times the thickness of the plate. And in general, if there are n bolts or rivets, the bearing stress would be the load divided by the number of bolts or rivets times that projected area, which is the diameter times thickness. So that's the imaginary body of the bolt or rivet. And that's the projected area, which is equal to diameter times thickness of the plate. So that's the bearing area, projected area. So sigma sub P, bearing stress, sigma sub P, is equal to load P over, in general, N times diameter times thickness, where diameter times thickness is the projected area of one bolt or rivet, and N is the number of bolts or number of rivets. Then if we have a body here subjected to these forces, if we reveal a section, then on that section acts the internal force systems, which consist of the normal force, the shear force, and the bending moment. So considering the left portion of the section, this is the free body diagram. So we have shear parallel to the section, normal force which is perpendicular to the section, and the third one is the bending moment N. So the normal stress is this normal component of force over the area of that revealed section. The shear stress is equal to this shear force D divided by the area of that section. And lastly, we have bending moment M, and that is N. And therefore, the bending stress is in general My over I. So that's it. The maximum value would be when Y is also maximum, and that happens at the outermost fibers. This bending stress is either tension or compression, depending on the configuration of the deformed shape of the body. Then another concept on stress is the punching shear stress, and we will call that tau sub P. So if you have here a puncher of diameter D and the punching force is P, so this is the plate where it may be a coin making puncher. So this is cylindrical of thickness T. So there's resistance to that punching force, and that is shear force because it is parallel to the lateral area of the cylindrical portion. Now, to help visualize the situation, we have here the coin or this disc here. The punching shear stress develops around this lateral area of the cylindrical plate or disc, and this P here should be divided by the lateral area of the plate, which is circumference because it is just rectangular, where the length is the circumference of this uh, disc, which is pi times diameter, and times the height, which is the thickness in this case. So punching shear stress therefore is equal to P divided by circumference pi d times thickness d. So tau P equals P over pi dt. So remember, we have here the bearing stress P over N times projected area diameter times the projected area per one bolt or per one rivet. So next, I define uniaxial loading and some expressions for the strains and stresses, normal stresses, as well as the definition of the what we call Poisson's ratio. So we define Poisson's ratio as the ratio between the lateral strain to the longitudinal strain. Since if the longitudinal strain is positive, or the force is causing the member to elongate perpendicular to that dimension or direction, the section will contract. So therefore, because Poisson's ratio is positive, it must be preceded with a negative sign. So the ratio of transverse strain to longitudinal strain is called Poisson's ratio. And to demonstrate, let's have this specimen or material and the coordinate axis. So let us say this is the x, the y, and the z axis. And the load is tension. The loads will cause the material to elongate because the loads are applied to elongate the materials. So we have tensile forces. So by the definition of Poisson's ratio, the Poisson's ratio is equal to, so along x it elongates positive strain, but along y and z it will be negative. Therefore, if the strains in the direction y and z is or are denoted with epsilon sub y and epsilon sub z respectively, then Poisson's ratio denoted by v like letter, is equal to the negative of strain y over strain x or negative strain z over strain x. So negative of strain y over strain x or negative of strain z over strain x. Again, the negative sign is preceded because if we have positive strain along x-axis, because the body elongates, then along y and along z we have contraction. That's why the strains there would be negative. And Poisson's ratio is positive. So to make it positive, a sign, negative sign is preceded. Anyway, strain y and strain z would be negative. And along x, because this is purely normal and axial, so from stress is proportional to strain, so normal stress along x, or yes, along x is equal to modulus of elasticity times strain along x. So that this would be the relations or definitions of Poisson's ratio and normal stress along x that could be developed. So stress is equal to proportional limit or Young's modulus of elasticity times strain. So shear stress also within proportional limit should equal to E is replaced by G, the shear modulus of elasticity, times the shear strain, which is denoted by gamma. So they are ironically the same. So for shear stress, it is equal to this shear modulus of elasticity times strain. Then the relationship or the formula for computing this G here in terms of E, it is equal to E whole over Poisson's ratio V quantity 1 plus Poisson's ratio. So E all over 1 plus Poisson's ratio. G is E over 2 times quantity 1 plus Poisson's ratio. So that's the value of G in terms of E. But I suggest that we cross multiply and write the formula as 2G quantity 1 plus D 1 plus Poisson's ratio equals E, so that you just read the formula to give, it's like that, sounds like, or it looks like that. 2 give equals E. 2 give. The formula 2G quantity 1 plus Poisson's ratio equals E. So this is my suggestion. 2G quantity 1 plus V equals E, so that you can read the formula as 2 give. So that it's easy for you and us to memorize the relationship between the Young's modulus of elasticity and the shear modulus of elasticity. So what are the expressions, formulas that we can develop when we have uniaxial loading? Just like that. So for uniaxial loading, the formulas would be strain along y equals negative Poisson's ratio times strain along x, and strain along z is the same, and this relationship here. So strain along x is sigma x from this equation, sigma x over E, while strain along y and z equal to negative Poisson's ratio times strain along x. But since strain along x is sigma x over E, this is supposedly negative Poisson's ratio strain along x from either of these two formulas here. So negative Poisson's ratio strain along x, but strain along x is sigma x over E. So this is the formula for strain along y and strain along z. Negative Poisson's ratio, normal stress about the x-axis or on the x-axis divided by Young's modulus of elasticity. Then if we have an element here which is subjected to the following stresses, normal stresses, sigma x for uniaxial loading, and if we have for biaxial loading, we have also sigma y. Both are tensile stresses. So take note that the effect of sigma x tensile would be to contract along the perpendicular dimensions. So perpendicular to the z-axis, so the strain is negative, and along y the strain is also negative due to the effect of sigma x, and we use these results here to develop expressions for strains and normal stresses. So if that's the z-axis for biaxial loading, so we have strain along x is sigma x over E, that's positive because this is in tension, but along y and along z that would be negative. So strain x over E, then plus this negative Poisson's ratio sigma x over E. Same is true along z-axis. So sigma x is equal to uh, strain x rather is equal to sigma x over E, then minus Poisson's ratio sigma y over E. So strain along x is sigma x over E in that direction. Then along y, the effect would be negative, and it is negative the effect in that direction, negative Poisson's ratio times sigma y, because we are talking about stress about x divided by E. So sigma x over E, positive, then along the y direction, it's negative strain, Poisson's ratio, sigma y, because in the y direction, over E. Strain along y is along y. We have a stress which is tensile also, which causes strain along the x-axis to be negative. So this is the resulting strain due to sigma y, positive sigma y over E from here. Then the effect of sigma y would be to have negative strain along the x-axis. And since it is along the strain axis, the strain along the x-axis, so we have negative Poisson's ratio sigma x over E. That's the contribution of the strain due to sigma x along the y-axis. So sigma y over E positive, then negative Poisson's ratio sigma x over E. Then along Z, since there's no stress here, it will be the combined effects of sigma x and sigma y, which will be negative along the Z. So it is negative sigma x times Poisson's ratio divided by E. Then the effect of sigma y is to cause contraction along Z also. So negative Poisson's ratio sigma y over E from this formula. Therefore, from here, we can develop expression for sigma x strain along x. Rather, if we factor out E is quantity sigma x minus Poisson's ratio sigma y times E. Sigma y is strain along y is 1 over E, quantity sigma y minus Poisson's ratio sigma x. Then along Z, because both are negative, so we factor out negative Poisson's ratio over E, and we have sigma x plus sigma y. Now from this equation, sigma x is strain along x times E plus Poisson's ratio sigma y. So sigma x is strain in x plus strain in x times E, which is that, plus Poisson's ratio sigma y. So plus Poisson's ratio sigma y. So that Poisson's ratio sigma y is then replaced by, this is the Poisson's ratio sigma y over E, where sigma y over E would be equal to, so strain sigma y is Poisson's ratio times strain along y. So Poisson's ratio times strain along y, that is from this equation. So strain in x times E, then plus Poisson's ratio times sigma y, and we replace uh, sigma y by modulus of elasticity times strain y from this relationship. So sigma y is E times strain along y. So E times strain along y. So take note. So Poisson's ratio transpose to the left, that's plus. Then strain y, E is like sigma times y. Then divided by 1 minus v squared. So divided by 1 minus v squared, it's because if we expand, so sigma y, for example, is equal to, we pattern it from here, strain along y plus Poisson's ratio strain x times E over 1 minus v squared. And that comes from sigma y equals E times strain y. From here, we multiply this by E. Then strain y E, which is that. Then transpose this to the left. So we have plus Poisson's ratio sigma x. Then we replace sigma x by this expression here. So sigma x is also strain from here times E, strain in x times E plus Poisson's ratio times sigma y. So that's sigma x, therefore is E strain along x plus Poisson's ratio, and we replace sigma y by its equivalent. Sigma y is equal to uh, E strain y plus Poisson's ratio sigma x. So where is this coming from? From here. So if we factor out sigma x, take note we have sigma x equals E times strain along x plus T E strain y plus V square sigma x. So factor out sigma x, and that's why we have 1 minus Poisson's ratio square equals E, factor out E for these two terms here. Then we have strain x plus Poisson's ratio strain y. So that's why sigma x is now equal to this. Factor out E, so strain x plus Poisson's ratio strain y, E over 1 minus V squared. Likewise, we pattern that result from here, and that's the result for sigma y also. Strain y plus Poisson's ratio strain x times E over 1 minus Poisson's ratio squared. Now for triaxial loading, just pattern it here. So strain x is sigma x over E. So imagine we have tensile normal stress along Z. So the effect of that would be to cause contraction along X. So we just extend this to strain X equals sigma X over E, then minus Poisson's ratio sigma Y over E minus Poisson's ratio sigma Z over E. So 1 over E quantity sigma X minus Poisson's ratio sigma Y, then minus Poisson's ratio sigma Z. If you factor out negative Poisson's ratio, because this is extended to Poisson's ratio sigma Z over E, and that would be the result. So next, for strain along Y, we pattern it also from here. It is 1 over E quantity sigma Y minus Poisson's ratio quantity sigma X plus sigma Z. Then strain along Z is 1 over E sigma Z minus Poisson's ratio sigma X plus sigma Y. So I hope that you are able to anticipate these results. So that these are the formulas for triaxial loading. Then if you want to compute for sigma x, sigma y, sigma z, we'll just manipulate these formulas to derive or solve for these stresses. So let's now have series of examples applying the formulas and principles already presented. So for problem 1, a compound bar consisting of bronze, aluminum, and steel segments is loaded axially as shown. Determine the maximum allowable value of letter A, P if the change in length of the bar is limited to 2 millimeters and the working stresses prescribed in the table are not to be exceeded. The maximum load in the bronze bar, the actual deformation of the bar. So we compute for P based on strength and based on this limited deformation of 2 mm, which is either positive 2 or negative 2, depending on the axial force diagram. So these are the properties of the different materials. So we draw the axial force diagram, away tension as positive and compression as negative. So it begins with positive 2p, then minus 4p, so negative 2p. So this member aluminum will be in compression. Then minus p, so negative 3p. That's why it balances by that 3p there. So based on strength, let's begin with um, force over area, normal stress. So if we consider the bronze, the load is 3P. So sigma is FL over AE, force length over AE, take note. So 120, this is the allowable stress, working stress for bronze, 120, and the load is 3P, compression. The area of the bronze is 450, so solving for P, it is 18,000 newtons. For aluminum, it is 2P. The load, the allowed working stress is 80, so 80 equals 2P over area of the aluminum, which is 600. 2P over 600, so P is 24,000 newtons. And for steel, it's the same load, 2P, but tension, and working stress is 140, so 140 equals 2P over area, which is 300. So solving for P is equal to 21,000 newtons. Therefore, the safe value of P is the lowest among the three based on strength. So it is 18,000, but we differ that answer yet because we have to um, evaluate the value of P based on deformation. So deformation plus minus 2 mm is equal to the sum of the individual deformations of these materials. 2 are in compression, so 2 will be negative and 1 is positive, 2P. So 2P for the bronze, for the steel rather. Let's consider the positive deformation first. 2P, and length of steel is 800.8 meter or 800 mm divided by area of steel is 300 and modulus of elasticity 200,000. So the unit here, if P is in newtons, Newton mm divided by AE, area times A, so newtons, cancel newtons. So P is in newtons and this is consistent that it is in mm. Then for the bronze, negative 2P the load, length 1000 mm over area of bronze, area of aluminum rather 600. Then modulus of elasticity 70,000 megapascals. Then plus P of the bronze negative 3P, the length is 600 mm divided by area 450 and modulus of elasticity 83,000. So because the right side is negative, so we consider negative 2 equals, combining the value of the right side in terms of P, that's negative 6.9145 times 10 to the negative 5 of P. So solving for P is 28,925 newtons. Therefore, the safe value of P is 18,000 newtons and the safe value of P is 18,000 newtons or 18 kilonewtons. Now, for the maximum load in the bronze bar equals, it is 3P, 3 times 18, so 54 kilonewtons compression. That's the maximum load in the bronze bar. Then for the actual deformation, we just use this, then we multiply it by P, and P is 18,000 to make the actual deformation in mm. So the actual deformation is, it is a contraction and it is equal to negative 1.245 mm. So for problem 2, this came out in November 2013 and May 2013. Two wooden members of uniform cross-section are joined by the simple scarf ply shown. Knowing that the maximum allowable tensile stress in the glue is 517 kilopascals, determine the largest load P that can safely be supported. The corresponding shear stress in the splice, the maximum load P that can be supported if the allowable tensile and shear stresses in the glued splice are respectively 600 kilopascals and 400 kilopascals. Then fourth, if T is 5,000 newtons, calculate the maximum normal and shear stresses. And fifth, determine the angle between these maximum normal and shear stresses, shear stress planes. So first, I'll develop a formula for normal stress, direct normal stress, and shear stress. So let's draw the figure first. So let me finish the uh, animations first so that there is a synchronous narration and solution. So we have here the given figure, and I'll call the area, which is the area of this rectangular section 75 or 125 times 75. Let's project it here. Call that still theta. And the angle theta is the angle that the plane, inclined plane, makes with the horizontal. So let's have this FBD, so that's P. This is also P, vertical, to be in equilibrium, and let's resolve this P here into two components. One parallel, which is called the shear force. The other one is perpendicular, P sub n, which is the normal force. So if that is theta, the angle between the normal and the vertical is also theta. So take note that the normal stress is normal force divided by area, and the area is this area n. And in terms of area of the cross section of the member, that normal area times cosine of theta is equal to area. So sigma n equals Pn over area n. And area n is replaced by A over cosine of theta, the hypotenuse. And P sub n is P cosine theta. So sigma n is P cosine theta over area over cosine theta. Therefore, the direct normal stress formula for this member is sigma n equals P over A cosine square of theta. Now, the value of theta is the angle that the plane makes with the horizontal or with the area is not 60 but rather 30. So sigma n therefore is equal to P. Sigma n, by the way, is the allowable tensile stress in the glue, 517 kilopascals, or that is 0.517 megapascals, or Newton per mm square, equals P, which is unknown, divided by areas 125 times 25, then times cosine square of 30 degrees. So this is the area, 75 by 125. Solving for P, P is equal to 6462.5 newtons. For part 2, the corresponding shear stress in the splice. Shear stress is this V here, which is P sine theta divided by area N. Replacing area N again, so V is P sine theta and area N is A over cosine theta. So that becomes P over A times sine theta cosine theta. And by its trigonometric identity, sine theta cosine theta is sine 2 theta all over 2. So therefore, this is sine 2 theta over 2, this one. Therefore, this is the direct shear stress formula for that case. So shear stress is 6462.5 B from here, divided by 2 area 125 by 75, then sine of 2 theta, sine of 2 times 30 degrees. So solving for shear stress, it is equal to 0.2985 megapascals times 1000 to convert it to kilopascals, 298.5 kilopascals. 6.3, the maximum load that can be supported if the allowable tensile and shear stresses in the glued splice are respectively 600 and 400 kilopascals. So for normal stress, use that formula to find the maximum load P that can be supported. So let's solve P from this normal strength available and P for shear stress, whichever controls. So 0.6 equals P over area 125 by 75 times the cosine square of the angle 30 degrees. Solving for PP is 7,500. Likewise, for shear stress, it is equal to 0.4 megapascals, while shear force over area, 125 by 75, sine of um, 2 sine of so this is normal. Sine of 2 theta, sine of 2 times 30 over 2a. So 0.4 equals P over 2 area, then sine of 2 times 30 degrees. Solving for PP is 8660 newtons. So the lower value is the safer, therefore P is 75, P is 7,500 newtons, less than equal to 7,500 newtons. Then for third question, so for shear controls, we have 0.6, so 0.4 equals, so use this formula here, P over 2A. That's why we have 7,500 newtons. It is 8660 based on shear, but the lower value is the safer, so that's why P is less than equal to 7,500 newtons. Tensile strength of the wooden bar is the controlling factor. AP is 5,000 newtons. Calculate the maximum normal and shear stresses. So our maximum normal stress formula is this, and this is maximum if cosine square of theta is maximum. The maximum value of sine and cosine is 1, and that happens when theta is 90 degrees. That is, the load is directly perpendicular to the cross-sectional area of the wooden bar. So substitute here, take note that we replace this by 1. So sigma max equals 5,000 times 1,000 to convert it to newtons. 5,000 newtons times 1,000 over area times quantity cosine square of something, which is 1. So solving for sigma max, it is 5,000 over quantity 125 times 75. We multiply 1,000 to convert it to kilopascal. So the answer here is in kilopascals, and it is less than equal to 533.3 kilopascals. The maximum shear stress formula, we replace sine 2 theta by 1 because the maximum value of sine function is also 1, and that happens when theta is 45 degrees. So that 2 times 45 is 90. That happens along the plane of along the shear plane. So this is in kilopascals. Sigma max less than 533.3 kilopascals. For shear stress, tau max, just P over area. And remember, it is half of this value. So P over 2A, you replace sine 2 theta by 1. So that's why it's 5. So that's maximum normal stress. Shear stress, substitute, we replace this by 1, so it will be 266.67 kilopascals. So sigma max P over A cosine theta n. This is maximum if cosine theta n is 1, and that happens when theta n is 0 degree. And for tau max, P over 2A sine 2 theta A, theta for shear, and for maximum value, this should be equal to 1, and that happens when sine 2 theta b is 1 or 2 theta b is 90, so that means theta b is 45 degrees. So theta B is 45 degrees. Therefore, the angle between planes of maximum normal stress and maximum shear stress is 45 degrees. So theta is 45 degrees. The force required to punch a 10 millimeter thick steel plate with an alternate strength of 450 megapascals is 280 kilonewtons. What is the diameter in mm of the puncher required? So formula for punching shear stress is load P divided by um, shear stress area, which is shearing area, which is pi dt. So punching shear stress P over pi dt, it is D, that is the unknown here. Allowable value is equal to 450 and P is 280,000 newtons, thickness 10 mm. Substitute. So 280,000 over pi dt. Solving for dd is 19.8 mm. Next, problem 4. A spherical pressure vessel 600 mm diameter is 6 mm thick and with internal pressure of 9 megapascals. The factor of safety with respect to bursting is 3. Determine the ultimate hoop stress of the material. So the ultimate hoop stress, the factor of safety is equal to the ultimate hoop stress divided by the working stress or the actual stress. The formula for actual stress for spherical pressure vessel is PD over 40. So definition, factor of safety, sigma T ultimate divided by sigma T actual, where sigma T actual is PD over 40. So substituting pressure internal 9, diameter 600 mm divided by 4 times the thickness 6 mm. So that would also be in megapascals. So that is equal to 225 megapascals. Therefore, substitute into this formula, 3 equals sigma Tu over 225. So sigma sub Tu equals 3 times 225 and that is equal to 675 megapascals. Problem 5 is occurred in May 1996. A metal specimen, 28 mm diameter, has a length of 450 mm. A force of 360 kilonewtons elongates the length by 1.5 mm. What is the modulus of elasticity in gigapascals? So from stress proportional to strain, so we compute the stress and the strain is deflection over original length, or deflection equals PL over AE, which is also stress length over E. So I just use this formula, 1.5 equals E, 360,000 newtons. The length is 450 mm divided by area, pi times 14 square. Be consistent with the units also. E is the unknown. So 1.5 equals 360,450 pi 14 square. This E here is in megapascals. So 175,395 megapascals. To convert it to gigapascals, we divide this further by 1000. Therefore, E is 175.395 gigapascals, or simply 1.5.424 significant figures. And lastly, we have problem 6 for this slide. A 25 mm diameter steel rod, 300 mm long, is subjected to a tensile load of 100 kilonewtons. If the Poisson's ratio is 0.33, determine the lateral strain of the rod. So lateral strain is the formula for Poisson's ratio is negative longitudinal strain divided by negative lateral strain, Poisson's ratio negative of lateral strain divided by longitudinal strain. So Poisson's ratio is negative lateral strain over longitudinal strain. We can compute the longitudinal strain because it is just force over PL over AE. So lateral strain is sigma over L and delta over L rather, and delta is PL over AE, or stress length over AE. So lateral strain, longitudinal strain is sigma over E, from sigma equals strain times E. So this sigma is force over area, and this E is 200,000 megapascals. So sigma force 100,000 divided by area pi 12.5 square, radius 12.5, divided by E, which is 200,000. So lateral longitudinal strain is 1.0186 times 10 to the negative 3. Then substitute here. Lateral strain therefore is negative Poisson's ratio 0.33 times this value here. It is equal to lateral strain is equal to negative 3.361 times 10 to the negative 4. The unit would be unitless, but you can make it meter per meter and m per mm depending on what you want that unit would be. Next, problem 7. Compute the value of the shear modulus G of steel whose modulus of elasticity is 207 gigapascals and Poisson's ratio of 0.325. So remember that the formula that I suggested is 2 give. So that means 2G quantity 1 plus Poisson's ratio equals E. So let's use that. 2G quantity 1 plus Poisson's ratio equals E. So we're looking for G, Poisson's ratio 0.325, and E is 207 gigapascals. So solving for G, the shear modulus 78.11 gigapascals. Problem 8. A steel bar 20 millimeters in diameter, 150 meters long, is suspended vertically from one end. Its specific gravity is 7.85, and at the free end is a 20 kilonewton load. If the modulus of elasticity is 200 gigapascals, compute the total elongation due to the weight of the bar and the total elongation of the bar. So we separate the elongation due to the weight and combine it with the elongation due to this axial load of 20 kilonewtons. Then the total would be the sum of the two. So for the due to the weight, so let's draw the figure to analyze the situation. So we have here the strip dy, then y from the free end, where acts P, tensile load. Then this portion here has a weight Wy, and the weight is equal to specific weight of this steel, which is 7.85 times 9,800 to convert it to newtons per cubic meter. The volume is cross-sectional area times y. So the constant force just below that strip and just above would be Wy. So differential deflection due to the weight is the force is Wy, the length is dy, divided by area times A. These are constants. Wy is specific weight gamma times volume, which is area times y. So differential deflection due to weight is gamma times area y. This is the Wy dy over AE. Can cancel area, and therefore deflection due to the weight is equal to 1 over E integral of y squared dy gamma over E integral of y squared integral of y dy, which is y squared over 2 from 0 to L. So formula would be gamma L squared over 2E. So substituting, gamma is 7.85 times 9,810. Length is 150 meters square divided by 2. Then this is E in pascals, which is Newton per meter square. The numerator is Newton per cubic meter times meter square. That would be Newton meter. Denominator is Newton per meter square. So the resulting unit is meter. That's why we multiply 1000 to convert it to mm. And it is equal to 4.332 mm. Then due to the axial load P, it is just PL over AE. So the total therefore is deflection due to weight and axial deformation, which is PL over AE. P is 20,000 newtons, length 150 meters, so Newton meter. Denominator is area pi 10 square, 200,000 newtons per mm square, because this is in megapascal. So the denominator is Newton, the numerator is Newton meter. So meter times 1000 to convert it to mm, consistent with this. So the total deformation is 52.08 mm. So for the next problem, we have an axial load of 120 kilonewtons is applied to a flat bar 15 mm thick, tapering in width from 120 mm to 60 mm in a length of 10 meters. Determine the total elevation of the bar if E is 200 gigapascals. So this has varying cross-sectional area. So we apply integral calculus here to solve for the total elongation of the tapering bar. So this is the figure. It is 120, 60, and 60 to 60. So if you draw a line parallel to this one side, so that's why we have 60 here. This is 60. Length from this zero end, considering this triangular part of the plate. So x differential length is dx, and let's call that y. Let's express y in terms of x. So the force here is P constant, and the length is originally dx. So differential deflection is equal to P dx over AE, where area is also a function of x. Area sub y, I'll call that area y. P is 20,000, 120,000 newtons. That's P. Area is width perpendicular to the board 15 times this total dimension, which is y plus 60. So y as 2x equals 60 mm as to 10 meters, but 10 meters is converted to mm also to be consistent. So y is 0.006 of x in mm. So that's why then area S is 60 plus y, quantity times 15, area y. So area y is 60 plus 0.006 times x times 15. So sigma x therefore is integral from 0 to 10,000 mm of P, which is equal to 120,000 newtons dx all over area 15 times quantity 60 plus 0.006x, then E is constant at 200,000 megapascals. So sigma x here is in mm. Sigma x is 4.621 mm. So problem 10. Here, horizontal steel square bar, 900 millimeters long, is 40 mm on a side. Initially, there is a gap between rigid walls of 0.6 mm. Assuming the initial temperature is 20 degrees Celsius and the coefficient of thermal expansion of steel is 11.6 times 10 to the negative 6 per degree Celsius, what should be the final temperature such that the resulting compressive stress in the bar is 60 megapascals. So E is 200 gigapascals. So remember that there is initially a gap between the free end of the square bar, which is 0.6 mm. Then the thermal expansion should be greater than this so that a compressive stress will develop. Then from that compressive stress, we can compute the corresponding deformation due to that stress. So remember that deflection by temperature change is equal to beta L delta T or balat. And from there, we can compute the uh, expansion supposedly. So delta due to temperature equals beta L delta T. Then we can solve delta T, where delta sub T to cause compressive stress of 60 megapascals in the bar should be equal to the initial gap, which is 0.6, plus the deflection due to the contraction due to this compressive stress. So delta equals stress length of the bar divided by modulus of elasticity, or PL over AE, but P over A is stress. So that's the formula for the delta due to that's compressive stress, and it is equal to 0.27 mm. Therefore, the thermal expansion should be 0.6 plus 0.27 mm. And we equate this to using this formula to solve for delta T. So the temperature should increase so that it will expand, the bar will expand, so that delta T point deflection due to thermal expansion 0.87 equals beta 11.6 times 10 to the negative 6 times 900 mm times delta T. So delta T is 83.33 degrees Celsius, so that the final temperature should be, this delta T is final temperature minus initial temperature, which is 20. So final temperature equals delta T final temperature minus 20 equals delta T. So therefore, final temperature equals 20 plus delta T. So it is 103.3 degrees Celsius. So for the next problem, 11, a steel bar 50 mm in diameter and 2 meters long is surrounded by a shell of cast iron 5 mm thick. Compute the load that will compress the bar a total of 1 mm in the length of 2 meters. Use modulus of elasticity of steel 200 gigapascals and for cast iron 100 gigapascals. So these two materials jointly support a load. So therefore, the total load that will cause 1 mm deflection is load on the steel plus load on the cast iron. And another important thing is that they have the same deflection. So for the steel bar, so take note this is hollow. So P equals P sub S plus P sub Ci. Then delta of steel is also delta of cast iron equals 1 mm. So for we equate 1 mm to force in steel, length of steel which is common to 1000 mm divided by area of steel which is pi 25 mm quantity squared and modulus of elasticity 200,000 megapascals. So 1 equals P of steel 2000 pi 25 squared 200,000, so that P sub S will be in newtons. So P sub S is equal to 196,350 newtons. Then for the cast iron, so the area of the cast iron is out area of big circle with radius 25 radius of steel plus this 5 mm thick of cast iron, so 30. Then the inner radius is back to 25. So 1 equals P sub Ci 2000 over pi quantity 30 squared minus 25 squared. Then modulus of elasticity 100,000 megapascals for cast iron. So solving for P sub Ci 43,197 newtons. Then the total load is adding 196,350 plus 40,197. So the total load is equal to 239,547 newtons in kilonewtons, 239.5 kilonewtons. So that's it for this uh, strength of materials 1 part 1.